In this video, I wanted to discuss how you can use trigonometric functions to solve the position of any point on an XY graph rather than just one on the unit circle. Because our conventional um, our conventional trigonometry was defined to keep us on a point which is directly on the unit circle, and I could use the cosine of t or the sine of t or tangent of t to figure out the properties of that specific point, whether it be x, y, or y over x or whatever. But the question also arises, what if I have a point that's not in the unit circle? How can I use sine, cosine, and tangent to find points and discover the properties of that? And it's kind of joining the idea of SOHCAHTOA with the unit circle and kind of just expanding our definition. And often what we refer to this as polar form or of a point, which is similar to the formulas which I was discussing when I was talking about right triangle trigonometry. It's like an alternative way I could look at the adjacent and opposite sides of a triangle. In that, notice that since the adjacent side, right, cosine of theta is adjacent over hypotenuse, so I could say that cosine theta is b divided by r. But if I took b divided by r and multiply across by r, that would give me b equal r cosine theta. This is the equivalent to SOHCAHTOA, the cosine part. Cosine is adjacent over hypotenuse. But in the same way, hypotenuse is equal to adjacent times the cosine of theta. Sorry, I said that wrong. Adjacent is equal to the hypotenuse times the cosine of theta, whereas the opposite side is always equal to the hypotenuse times the sine of theta. This is an alternative takeaway to SOHCAHTOA, just as a way of rewriting it, where essentially if you know the hypotenuse and an angle, this side you take the hypotenuse times the cosine. Basically, the cosine will scale back the hypotenuse to be the adjacent side, and the sine function will scale back the hypotenuse to give you the opposite side. And this would be like, it's different than the example we did, because in that example we used the tangent to function to find the height, but it's kind of like a way of starting with the hypotenuse to find either the base or the height of the triangle. But each one, that's what the sine and cosine functions do respectively. Cosine gives you adjacent, sine gives you opposite. But all that being said, I wanted to do yet another definition of trigonometric functions for a point on the xy coordinate outside of the unit circle. So say, for example, I take a point which is not distance 1 away, but just a point x, any point x comma y. What I wanted to reiterate is that it changes very, very slightly in its definition. And if we look at, we'll say, for example, what's the sine and the cosine of the angle that this point forms with the x-axis in standard position, notice that the definition shifts just a little bit. Because on the unit circle, sine was always y, cosine was x, tangent was y over x. Well, notice tangent is still the same, but what has changed is that sine is y over r, cosine is x over r. But really notice that the only difference is if I take any point on an xy graph, it's not necessarily going to be 1 away from the origin, right? Because if it was stuck on the unit circle, it had to be 1 away because the unit circle was hypotenuse 1. But if the hypotenuse is longer, we're just calling the hypotenuse r in this case, which is really common for with what we call polar form, where r just stands for radius. But basically, the sine would be, and notice this is consistent with SOHCAHTOA. Sine is opposite over hypotenuse. Cosine, SOHCAHTOA, adjacent over hypotenuse. X over r tangent, opposite over adjacent. It's just sort of like you can imagine taking a triangle and rooting it at the origin, basically putting the angle in standard position. And if we do that, it elaborates our definitions a little bit, and it allows us to think about other points, not just ones that are 1 away from the origin. So basically, instead of just being on the unit circle, this works for any point. So let's just look at a couple examples. I think you'll see how this is how this could be helpful. But let's say I have the point -3, 4. It says to find the trigonometric ratios, draw the triangle, and approximate theta. But essentially, if I'm given a normal coordinate point in the xy plane, I could graph that point, which is -3, 4. So that would be left 3, up 4. So my point would be over there in quadrant 2. Cool. So what? And also, we often refer to this as a rectangular coordinate. we're not going to really get into what we call polar coordinates in this class because we're not going to have time. But the polar coordinates are an alternative coordinate system where we're focusing on not what is the xy coordinate, but at what angle does this form in standard position and what radius. So basically, what would the hypotenuse be of such a triangle, and at what angle would this triangle form with the x-axis in standard position? But basically, what I could do is I could connect this point to the x-axis and form a triangle. And that's kind of the point which I'm getting at, is that this triangle would have a particular x value, y value, and r value, as shown in the diagram. And the angle, if it's in standard position, would connect back to the x-axis, and that would give us the theta that this triangle would form. Even if it was in quadrant 2, it would, it's still in standard position, which just means it's stemming from the starting position, positive x-axis, as we defined originally in chapter 4, right? That's always where we start arbitrarily, but that's just the beginning. Anyways, what is my point? Well, notice what I know is I know x and I know y. X was given to me to be -3, and y is 4. And it can seem a little bit strange to label the sides of a triangle with negatives, but in a context of a coordinate system, you can have distances which are negative and positive. It's because this is to the left, not to the right, right? We're distinguishing this triangle from the one in quadrant 1, which would have ratio 3 to 4, because this point is to the left instead. So it can make sense to have negative sides on the triangle. But essentially what I want to know is, well, what is theta? What is r? I could use SOHCAHTOA to do all of this using exactly the definitions I have above. Because, well, first of all, r's can be found by the Pythagorean theorem. So -3 squared plus 4 squared should be equal to r squared by Pythagorean theorem, which is 9. It's exactly the same math we did a minute ago. But that would be 25 equal r squared. So r would actually be taking the square root of both sides. R must be equal to 5. And actually, technically, the hypotenuse could be negative for an alternative triangle, which is something I don't want to get into right now. In polar coordinates, it actually is possible to have a negative hypotenuse. But I wouldn't really worry about that because, again, we're more focused on physical triangles with real applications. Anyways, but also, let's say I wanted to know theta. Well, I could use any of the trigonometric functions to do this because, well, I already know x and y. So basically, tangent of theta is always y over x, as it says above. So if I want to know theta, theta would be equal to the arctangent of y over x, and I could figure out what that angle would be. And if I use the proper negative signs, it's always going to be in standard position. But the little intricacies of the inverse function could give us an answer that doesn't make sense. And that's something I also wanted to revisit. But these are formulas which are often referred to as the polar formulas for how you change from a rectangular coordinate into a polar coordinate which is based on r and theta instead of x and y. But actually, I'm diverting from what the example said to do. So what I also said to do is find the trigonometric ratios, which basically all that means is, well, what is cosine of theta? What is sine of theta, and so on. Even without knowing theta, I know that cosine of theta is always x over r. Sine is y over r. Tangent of theta is y over x. And basically, once I know the three sides of the triangle, since for the point I knew x and y, I could always find r, and once I find r, I could then find each of the trigonometric ratios. And if I wanted to find the other three, well, secant is the reciprocal of cosine, cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. But basically, I could find all 6 of those ratios, and I could then use any one of these to find theta. But my point going back to finding actually theta, remember that the inverse functions will not necessarily give me the angle in quadrant 2. And actually what I would choose to do is I would choose to use the cosine here to find theta instead of the sine and tangent. And this was just because the arc cosine, if you remember, the range of the function was 0 to 180 or 0 to pi. It always gives me an answer that is is going to be in quadrant 1 or 2. So if I'm trying to find an angle in quadrant 2, it's going to give me the correct answer. And this is like my point here is that if I try to use the arctangent of theta, it's not necessarily going to give me an answer in the right quadrant. So let's solve each one of those, and I'll just try to explain what I mean here. But basically, let's look at what these answers give us and kind of talk about why they're different. Because as we can see from this location, each one of these is all based on the same triangle. So all these ratios should be correspondent to the same angle that I have drawn here. But the inverse functions, sometimes they give you the wrong answer, and this was not wrong answer, but it's in the wrong quadrant. This is something that we started to discuss before when we were talking about the range, and this is where it kind of comes back to bite us in a way that, you just have to think about, is this actually right or not? But if I do these calculations, the arc cosine of negative 3/5 gives me 126.9 approximately degrees. And that answer seems about right because it's in quadrant 2. So that's kind of why I was saying, well, I would use the arc cosine here because it's going to give me the right answer. But the arctangent is not going to give me the right answer. It's technically correct, it's just in the wrong quadrant. Notice that the arctangent will seem to disagree with the arc cosine, and it will give me a different answer here. But notice that this angle, negative 53.1 degrees, sorry, it's getting so messy, I'm trying to do too many things at once, would actually be in quadrant 4. Because, right, if I'm talking about a negative angle, negative 51.3 would be right down there. But notice it's actually the same angle, but opposite. And really, and that's because what the range of arctangent, if you remember we talked about, is from negative pi over 2 to pi over 2. It uses quadrant 4 and quadrant 1. So it's just going to give me the negative answer within its range, because it has to give only one answer because it's a mathematical function. And because an inverse function can't have two answers, it sometimes gives me the wrong answer. But I can obviously tell that that's not correct, and I could find the correct answer by using the period of tangent, which, since its period is pi, I know that it's going to be equal to the angle if I add 180 to this. If I add 180 to this, notice what that does is that gives me exactly the same solution, which is in the proper quadrant. And I'm saying that you could use the arctangent to find the correct answer, but you just would then have to figure out the period. And notice that if I'm looking at the diagram here, of course, the correct angle that I'm actually looking for is opposite of 180 to the answer that the calculator gives me. So that's how I would know why would I add 180 to that, because it's giving me the negative angle. If I add 180, it will put it into quadrant 2 where I want it. But let's just do one more example in quadrant 3. And also, if you're worried about all like finding the right quadrant, it's really not that big of a deal. It's not something that I'm gonna really trouble you guys with on the test, but it's just something to be aware of, that sometimes those inverse functions don't always give us the answer in the correct quadrant, and then we have to figure it out using geometry. Anyways, in the second example in the packet, it says assume that tangent of theta is equal to 2/3 and that theta is in quadrant 3. And this is a very plausible test question or homework question, and it's definitely a little tricky if you don't know how to begin. But basically where I would begin in these sorts of questions is begin with what I know and try to draw a triangle. So what I know is I have theta's in quadrant 3. So if I'm imagining that, I could imagine, my angle's over here in quadrant 3, and since it's in standard position, it would be stemming from the x-axis. It doesn't actually say it's in standard position in the question, but that's always implied with such a thing. And also, another thing, I don't really, if I'm trying to figure out this point, it should have an xy coordinate. But since I was given the tangent of theta, since tangent of theta is always the ratio of y to x, I could use that to figure out, what are x and y? Technically, I don't know, but I could just assume x is 3 and y is 2, since tangent always gives me that ratio. And notice that if I just, plug those in for x and y, that doesn't actually make sense, because in quadrant 3, That's not going to be, they're not going to both be positive, they're going to both be negative. And notice that if I use double negatives for -2 and -3, that actually ratio is positive, so that makes sense, because the ratio of y to x would be -2 over -3, and that would fit the original bill, as indicated. So basically, I could use the quadrant to figure out, okay, are those positive values or negative values for x and y? And they should, of course, be negative because of the quadrant that theta's in. But basically, it says to draw the triangle, find the other trigonometric ratios. But basically, since I know, my point is I know x and y. X is -2, y is -3. And I can find the hypotenuse via Pythagorean theorem, because a squared plus b squared is equal to c squared. Or I'll use x squared plus y squared is equal to r squared, which is, again, a formula that you will see in the definition of the trigonometric functions, which is another, what we often call a polar formula for polar coordinates. But what we'll end up with is 4 plus 9 is equal to r squared, which r squared is equal to 13. So r should be equal to the root 13. Again, technically plus or minus, but we can just assume the hypotenuse is positive. So what I get is the third side. I could even approximate it or just leave it as exact, because it says to find the other trigonometric ratios, and if I just leave it as root 13, it will be more exact. So say, for example, I want to know, well, what's the cosine of theta, or what's the sine of theta, or, etc., cotangent of theta, cosecant of theta, and the secant of theta, the other 5. Once I know all 3 sides, that's it. I just need to find the third side, and I'm golden. But basically, the cosine is, well, you could use SOHCAHTOA, because SOHCAHTOA is the same as this, or you just use the fact cosine is x over r. Cosine is -2 over root 13. But the thing about using SOHCAHTOA is you might miss the fact that cosine should be negative in quadrant 3, because if we're in quadrant 3, we're to the left, cosine's got to be a negative. And notice that if I actually draw the triangle, I can see that. But if I just use this information and I don't notice, excuse me, that it's in quadrant 3, I might overlook that. The sine of theta is opposite over hypotenuse. And so, again, negative because we're in quadrant 3. The cotangent is x over y, which is just 3 over 2, or the reciprocal of tangent. So that one's, I didn't actually need to do any work to find the cotangent because I already knew tangent. But the cosecant is the reciprocal of sine, so that would be negative root 13 over 3. And the secant is the reciprocal of cosine, so root 13 over 2. And basically, I can find all the ratios. And I could use any of those ratios to then find theta. But notice that since I'm in quadrant 3, actually none of the answers would be correct if I used an arc function. Like, say, for example, I used the arc sine to solve for theta. Theta would be equal to the arc sine of negative root 3 over 13. This would actually give me an answer in quadrant 4 instead. Or say I was to use the arc tangent, which is actually what I would probably recommend doing. And again, how I know which one to use is all about which one's easiest. But if I just start with tan theta is equal to 2/3, what I would get is that theta is equal to the arctan of 2/3, which is going to be in quadrant 1, because arctan only gives us answers in quadrant 4 and quadrant 1 based on its original range. And obviously, none of the functions are going to give me an answer in quadrant 3, so I'm a little bit stuck from initial in solving that theta. None of them are programmed to work properly. But what I could see is that the arctan of 2/3 is 33.7 degrees. Obviously, that's not correct for this angle. But if I just add 180 to it, since tangent's period is 180, I usually find using the arctan pretty easy way of finding the proper angle, because if it's not the right answer, all I need to do is add 180 to it, because really what the arctangent of 2/3 would give me is the solution in quadrant 1, which is the same triangle but positive. And the secondary answer is just going to be across the triangle plus the same exact symmetry, the same exact slope, just opposite, which is always supplementary to that across from one. Basically, you add 180 to it, not supplementary. That means something different, but similar. Anyways, let me wrap this video up because it's getting way too long. But basically, if I actually wanted to solve what that angle is, notice I didn't actually even ask you that, but I'm going a little bit above and beyond here just to really solve everything I possibly could. That angle should be 213.7 degrees in that case.